Thanks everyone for coming. My name is Yilei. I graduated from Boston University and now working in Visa Research for a year. So Visa Research is a lab next to Stanford in Palo Alto. So we have basically two teams. One is doing security and crypto, one is doing AI. So I'm from the crypto part. So just a brief introduction of myself. So I did undergraduate at Georgetown University before going to Boston University. At Boston University, I work mostly on lattices, multilinear maps, and obfuscation related projects. So if you also work in multilinear maps or have heard about this concept, so this is a topic which is like being popular starting from 2013, which is also roughly when I started my PhD. And I work mostly on both attack and proving secure stuff from multilinear maps. So the reason I later look at algebraic geometry since my last year of PhD is mostly of the multilinear application we want to prove that don't really work with a proof of security or or maybe they can be able to, they can be completely broken. So I tried to look a little bit on elliptic curve and algebraic geometry during my last year of PhD, which is also suggested by the original paper of multilinear maps by Bonnet and Silverberg. They say if an OM multilinear map is computable, it's reasonable to expect it to come from geometry, like the bilinear case for Weyl and Tate pairings. So that's what drives me to the topics of elliptic curve. Originally, I tried to omit everything from isogeny because to work on elliptic curve itself, it's okay not to jump from one curve to the other. And later I realized this is a concept which is very interesting and unavoidable. That's what leads to me to this paper with my co-author at Boston University, Salim Ali Attu. So Salim is a researcher from BU Maths Department. So he's interested in teaching crypto. That's why we are working together. So right now I'm a researcher at Visa Research doing mostly post-quantum crypto, and the lattices and isogeny are both relevant. So in Visa Research we also have KU Leuven alumni Atul, who also graduated from here. So he worked on symmetric crypto, and I think that also introduced me to KU Leuven, and I decided to pay a visit here before TCC. So after the introduction, let me move on to the main topic. Today I won't talk about anything with lattices, but if I have interesting topics about lattices, multilinear map, we can talk offline. Today let me talk about some weird creature from group, like a Diffie-Hellman group. So let's look at the traditional group we study about a group which we believe that discrete log problems are hard. The famous examples include the multiplicative group of a finite field, and the elliptic curve group, also ideal class groups, and you can make other examples. In some sense, they are just a different representation of the trivial looking Z mod NZ group, like a trivial looking group where no discrete log is hard. They just give a different representation of the naive looking group. And in the later few slides, I will use the bracket to denote a representation of a group. Let's look at one of the common features of the example I gave. If you give any representation of a group element in the previous group I gave as example, although computing discrete log is hard, but it is always easy to compute the representative of the inverse element of the group. For example, in the multiplicative group of finite field, if you are given the representation of element A as g to the A mod q, it's always easy to compute g to the inverse A by just taking g to the A as a whole integer and do the inverse over that ring, and you get the g to the inverse of A. You can also observe the same thing over the other two examples. So how about coming up with a group with infeasible inversion? So let's define what it means by a group of infeasible inversion. So a group with infeasible inversion requires that giving a representation of an element x, it's infeasible to find the representation of the inverse of x. So this is the most important property you require for a group with infeasible inversion. We also require that composition of group elements are still easy. Say, given the representation of x and y, it's still feasible to compute x plus y. And with these two, if you can come up with such a group with these two properties, it's motivated in the thesis of Hohenberger and Molnar of respectively their master thesis and bachelor thesis. They say that if you can come up with such a group, then you can have some application of creating a directed transitive signature. But there's also a more intuitive application later found by other researchers, Irrer et al., called broadcast encryption. I will introduce this example later. But in their thesis, they didn't propose any candidate group representation which have the property that inversion is hard and the composition is easy. This is a thesis done when they are both advised by Revest, and they look into different groups and they say none of them works. But if you find such a group, there is such a property. There is such an application. Let me give you the example of broadcast encryption. So say if you have abstractly any group representation which satisfies this property, how do we do efficient broadcast encryption? So the public parameter of, so let me briefly say what is a broadcast encryption. The broadcast encryption, the purpose is you want to distribute the content to many users, but when you encrypt it for once, you can encrypt it with a subset of all the users, such that only the user in the subset are able to decrypt. The users who are not in the subset are not able to decrypt. The whole point is to have the ciphertext size proportional not to the number of users, but only proportional, for example, to the security parameter. Because otherwise there's a trivial solution, just encrypted under everyone's different secret key. So let's see how do we use a group with infeasible inversion to do efficient broadcast encryption. So the master secret key is a representation of a secret element S. And for each user, let's say user 1, 2, 3, 4, let's denote it as user I. Each user has a public key and a secret key. The secret key is the master secret key plus a random number Ri, give the representation. And the public key is simply the representation of the random number secret. Let's see how to do encrypt under a subset. So to do encrypt under a subset T, you pick the encoded element in all the public keys plus the master secret key as use the representation of this value as the encryption key, and then let the ciphertext be the encryption of any symmetric key encryption using this key and to do the encryption. So let me give an example. If you want to encrypt it under user 1 and 2, you just pick R1 and R2 and RS as use the representation of this key as the symmetric encryption key. So to do decryption, you can see if you are a legit user, you can see your own secret key and the set of who else is in the set. So you take your own secret key S plus R and then take the public key for the rest of the people in the set. So for example, if I encrypt under user 1 and 2, you are user 1, you take your own secret key and take user 2's public key. Then you compose, you can recover the representation of the encryption key. But if you are user 3, you don't have the element called S plus the necessary element in the group. So at least by functionality, it's hard to recover such a key. Let's give a brief intuition of security. So suppose, because remember, we are going to use the fact that it's infeasible to invert and it's easy to compose, right? Let's say suppose it's easy to invert. Then what you can do is pick your own key, public key and the secret key pair. You do secret key subtract public key by inverting the public key itself. Then you can recover the master secret key. So after you recover the master secret key, you can do whatever you want. So at least intuitively, you need a group with infeasible inversion to have naive security, and you need composition to be able to decrypt using other people's public key and compose with your secret key. Formally, actually, Irrer et al. Gave a formal proof. Say if if the underlying thing is a group with infeasible inversion, then it implies the underlying encryption is a broadcast encryption. In other words, if you can break the broadcast encryption, you can invert a group element in the group. Let me also remind that broadcast encryption with such succinctness. So let's observe here the succinctness is if the key is succinct, like the representation is very compact, then essentially everybody's secret key and the public key parameter are only dependent on security parameter, and the encryption overhead is only dependent on security parameter. But encryption key, broadcast encryption scheme with such succinctness is also known from bilinear map. Actually, chronologically, it's published 1 year later than 2004. But anyway, you can do it with bilinear map. So still, I think this gives a very simple conceptual example of something that if you have a grouping with infeasible inversion, it's very simple to achieve something very useful. Okay, so after I give the simple example, let me also explain some intuitive attempts you may want to try to find a group with infeasible inversion. So one of the intuitive example I was thinking about in the beginning is the following. So how about let the group be the multiplicative group in the exponent of the finite field Diffie-Hellman? So by that I mean, suppose we define the inverse of g to the a not as g to the minus a, but as g to the 1 over a. Then given g and g to the a, finding g of g or g to the 1 over a is also hard in many groups. It doesn't have to be mod RSA Moduli. But it turns out that multiplication in the exponent is also hard. So it's not clear how to do composition efficiently. And I also have tried other groups. So there are a lot of candidates where computing the inversion is actually hard, but the composition is hard at the same time. So it's not really useful for the applications mentioned in the previous papers. So this gives an example where actually composition fails. So how about I make another attempt based on the previous example. Say, right now I have a candidate where inversion is hard. Let's facilitate the composition part. So how do I facilitate the composition part? I obfuscate the multiply in the exponent circuit. So what do? For an encoding A, I give the first part g to the A normally, and I also give an obfuscated circuit with key as A and N to take whatever input you want. I raise it to x to the 2a. Let's forget about the 2 for mod. Raise it to x to the a, mod n. And in fact, Yamakawa et al. Has already proved, assuming I/O, you can show that when it's raising x to the 2a and when n is an RSA moduli, this obfuscation does hide a. And in fact, it can prove something with formality. So the formal answer is, if you assume I/O exists, then there is a candidate group with infeasible inversion, but it requires I/O, which is first inefficient, and then having a safe candidate is difficult. So in this work, we propose a candidate group with infeasible inversion from hard problems on elliptic curve isogeny graphs defined over RSA moduli. In other words, this is a candidate without using I/O and with a natural group representation. So this almost summarized the introduction. Let me give you a brief overview of how the idea follows. So here's the roadmap. It takes 5 steps. I will try to explain all the steps if time allows, but only if we explain a few points, it's already worse. So for people who are not familiar about isogeny, this is really the last most interesting slides, because later it will come to isogeny. It will be very technical. So here's the main idea. First, elliptic curve isogeny can be used to can be represented by a graph, and we are going to define some graph problem. And we are going to use the isogeny graph to represent a group, which is also coming from the isogeny capability. So the previous two parts are the mathematical background. The third line is over finite field, searching for close neighbor on the isogeny graph is easy. So this is the first time we are involving a computational problem. So the next 2 points are our contribution. The first 3 points are already known. So we observed that over an RSA modulus, previously what is easy in the finite field becomes plausibly hard. And then we use the plausiveness of certain graph problem to translate it into the hardness of inversing a group element using the connection of isogeny and the group. So that's the overall idea. The hope of this talk is to at least explain the graph problem clearly, and then go to the group will be very involved. So that's the overview of this talk and the basic roadmap of our ideas. So the plan of the rest of the talk, we have finished the first part, which is the overview. Then the second part, I will give a brief background of elliptic curve isogeny graph, which are necessary for this talk. And this part is all depend on previous work. I'm just gonna pick whatever necessary to us. And the third part is our contribution, is to define what is the isogeny graph over RSA Moduli and identify potential part problems. I think the graph problems are more or less over independent interest, independent of the underlying group itself. All right. So let me continue to the second part. Let me first recap some basic knowledge of elliptic curve. So elliptic curves are elliptic curves, and the simplest way to represent elliptic curves is by the coefficients of the Weierstrass polynomial a and b. So after you have a and b and q, you can uniquely identify an elliptic curve. Also, just to confirm a previous statement I make, like over elliptic curve group, computing the group inversion is easy, right? So otherwise we don't need to come to the isogeny business. So for elliptic curve group, you compose by picture, taking a line, intersect, and then reflect. This is the group operation. Taking the inverse is really easy. At least in the Weierstrass model, you take the point represented by x and y, and the x inverse y is in fact the inverse of the group element of P. Okay, so let me also define the J invariant of a curve. Whenever you are given A and B, a naive way of defining J invariant is by such a polynomial. A J invariant identifies all the isomorphic curves over the field. So if I'm working with elliptic curve over a complex field, all the curves with the same J invariant are isomorphic. Over the finite field, they are either isomorphic or the twist of each other. And in this talk, we are going to think about the curves with the same J invariant over the finite field. We just think about them. They are all the same for simplicity. They are all isomorphic for simplicity. Okay, so let's move on to isogeny. So before defining isogeny, so what is isogeny use? So you can study elliptic curve by taking a curve, defining, fix your A and B and Q, and study the group structure, how many points are there on it, and how does it look like on the graph. It turns out you can also study all the curves with similar structures all together. And turns out isogenous is a nice way to give a concept of similar other than isomorphic. So isogeny is not isomorphic. So what is an isogeny? The formal definition of isogeny is a morphism from elliptic curve 1 to elliptic curve that maps the O points on E1 to the O points on E2. In this talk, I'm not going to go to this formal definition, but rather let's use a more computer science way to think about isogenous. So Tate proved that two elliptic curves over a finite field are isogenous if and only if they have the same number of points. So as long as you can efficiently compute how many points is there on the elliptic curve over a finite field, you can identify whether they are isogenous or not. So if you fix a Q, Hess theorem says the number of points can be varied from q plus 1 minus 2 square root q to plus 2 square root q. So it's still a sub-exponentially large space, but Skov gave an algorithm that takes a and b and q in polynomial time, computed the number of points. So it is indeed, we can decide whether two curves are isogynous, at least in polynomial time. So just a little bit more explicit about how the isogeny look like. So suppose you have a curve E1 and a curve E2. Isogeny is a map. You can always write the map as a polynomial that takes x from E1 to the x on E2 and the y on E1 to the y on E2. The polynomial looks as follows. And the degree of the isogeny is the degree of this polynomial, or in other words, the polynomial is surjective. The degree is the size of the kernel. Just more explicitly, so suppose you have curve E1 and E2, then you can really write down the polynomial in details, writing the kernel first, then write down the map. You can see the degree of this isogeny is 7, and just as an example to have some concreteness to begin with. All right, so let me come to the more interesting observation about volcano. So it turns out if you put an isogeny, represented isogeny by a graph, where think about each vertex as one isomorphic class of elliptic curve. In other words, each vertex can be represented by a J invariant, and each edge as representing, if you fix a degree L, say L equals to 3 or 5 or 7, then if they're connected, it means there is a L degree isogeny between them. Then the left graph means if you fix the degree L, then the relation of all the isogynous curve look like that. So they kind of look like a volcano structure if you look from the top to bottom as a volcano. So the middle part is the crater, and you can also go downhill on the volcano or go uphill. So when I was preparing the slides for the first time, it's kind of close to Halloween. I was wondering why don't they think about this graph as a spider net. Right? So then I watched the spider net. You can see spider net are actually connected in the middle, right? So, and this graph is different. It's a volcano. The middle part is empty, right? So that's a way to remember it. So this is, the left part volcano is when you fix a degree, and you can see the structure from top to bottom. If you vary the degree, say you put a degree 3 and a degree 5 together, and if let's focus on the crater, then the connection relation may be as the following. So the 3 isogeny defines the crater, but they are also connected to each other in the middle by another degree, say 5. So this gives the brief structure of how the isogynous curve relate to each other. This relation is first described in the PhD thesis of Kohel, and the term isogeny volcano is later introduced in a later work. So let me right now mention the relation of isogeny graph, isogeny, and the group. So remember, eventually we are going to construct a group with infeasible inversion, and we are going to move from a hard problem on an isogeny graph to a harder problem on a group. So let me now describe the relation from the isogeny graph and the group. So if we fix, let's just to look at the crater, it turns out there is a group action defined on all the elements, for example, on the same level of the isogeny graph. And the group action is faithful and transitive on the set. The set is the set of all the vertices with all the same endomorphism. So right now I didn't define endomorphism, I didn't define what is the ideal class group, but let me make an example in the next slide. So here is an example of a crater of the isogeny graph over a field 83, everything mod 83. And these 7 J invariants are the J invariants or the isogynous curve, and they are all connected to each other by degree 3 isogeny. So we are going to use this graph to represent one group of size 7. So one way to represent it is the following. So if we let the J0, this J invariant, represent the identity in the group, so if you fix the identity, then there is a unique way to represent all the group elements in that group of size 7. So suppose we say A is the group represented by J1. So use one J invariant will uniquely represent one group element. Then the opposite way of the opposite J invariant J6, if you flip it in that way, work in that way, it will represent the inverse of A. So this gives one way of representing the group element in the ideal class group using the J invariance in the isogeny graph. All right. So far I have covered the mathematical background needed for understanding this talk. So now let's move on to the computational part. We're going to define a graph problem. Okay. So whenever we come to the graph problem, the natural problem to ask is how hard is it to find the neighbors? How hard is it to find some other points? Right? So let's first look at the neighbor search problem. So if you are given a polynomially large degree, so even very small degree, say 3 and 5 and 7, and you are given a starting curve, say E1, you can ask, how do I find all its neighbors? So in the literature, there are basically two ways of finding all its neighbors. The first way is you can find, try to find the kernel of the isogeny map, and then from the map you can build the whole map. From the kernel you can build the whole map, and then find the endpoints. This is called using Velours formulae. I will not discuss in detail of this method in the talk. The more interesting way of finding all the neighbors is by solving something called a modular polynomial. A modular polynomial is a global object that has take two variables. If one of them is E0, the J invariant of E0, then the other roots are the J invariant of all the other neighbors. So let me go to this method for more detail. So a modular polynomial of for degree L, so you can define it for all the degree 2, 4, 3, 5. Its parameters pair of elliptic curve related by an L cyclic isogeny, basically an L isogeny. And the modular polynomial takes two inputs, take two J invariants, and it outputs 0 if and only if they are the J invariants of L isogenous elliptic curve. So in this example, let's ignore this sentence. In this example, if you take a modular polynomial and mod 83, and take one of the input as 15, take the degree 3 modular polynomial, then the two of the roots are 48 and 71. Maybe there are other roots. What we know about modular polynomial is it can be defined over integers, and actually all the coefficients are over the integers. And it has degree L plus 1 for prime L, which also means the number of L isogeny neighbor is at most L plus 1. So in theory, all the modular polynomial can be computed in polynomial time to L, which means all the polynomial degree modular polynomial are efficiently computable. In practice, this modular polynomial have very large coefficient. Let me give you one example. So this is the modular polynomial 2. As you can see, it has degree L plus 1, and it's symmetric. It has large coefficients. And this is the smallest modular polynomial. If you go on, like modular polynomial 71 needs take a large storage. And you can find all the modular polynomials from L to 1 to 300 online. And the later will take a large storage to download. So that finished the introduction about how to find neighbors. The conclusion is easy, and there's even two methods. So how about if we selected two random curves on the graph? So suppose the graph is not only have 7 points in the middle, but have many, many points over a general Q. So we know the crater size is roughly square root Q. So if you selected two random points on the graph, they should be very far from each other. So we can ask, are there an efficient algorithm that give you 2 points, say find an isogeny, or in other words, find a path from E1 to E2? This is actually conjectured as a harder problem, and it's even hard for quantum computers. And in fact, this idea was used in one of the isogeny-based key exchange. It's originally proposed by Covain and the other work early. And right now, one candidate of SIDH is used in the isogeny-based key exchange KEM. And there's also a recent proposal using kind of like a special case on the supersingular graph by one of the authors here. And it's getting interested for the closed quantum reason. All right. But in this talk, we are going to not use the quantum fact because we are going to use the RSA group. So we automatically lose the, the post-quantum privilege. But we are going to find something else interesting. All right. So right now, let me move to our contribution of what we discover over the hard problem in the isogeny graph over RSA moduli. So to define the isogeny graph over RSA moduli, there are two options. One is you can define by modular polynomial. Say I have two integers presenting, let's pretend they are J invariants. We assume they are connected if and only if the modular polynomial of degree L take them as input, output 0. So this is one of the obvious way to define that two integers are related by isogenous relation over a general modulus. There's also a much simpler way of thinking about the problem we are interested in, and this is the one we are going to think about during this talk. Let's just think about if we can efficiently find two isogeny volcanoes that are with the same structure. We just glue them together by taking the CRT relations. Say, they are roughly the same number of, not roughly, they are exactly the same number of integers on the same structure of the volcano. Then we glue 2 points together, and this will also define how to glue the rest of the points. So in this talk, let's think about the second case. But we will refer to the first case as the general case, the second case as the special case. All right. Okay, another example. So suppose you can find another structure with at least 7 points on the isogeny graph over field 173. And say if this is the way you number all the J invariants over there, then you take the CRT composition of the corresponding points, you get something over there. By the way, this example is taken from one of the previous papers that do the key exchange. This example is found by ourselves, and you can efficiently find more examples. All right, so now let's come to the main point of this talk. Let's now look back onto the neighbor search problem over an isogeny graph defined over an RSA moduli. So still, we fix a polynomial degree L, say L equals to 3 or 5, and given a curve by its J invariant mod n, is there a polynomial time algorithm that finds its L isogenous neighbors? So this is the problem we ask. By finding, let's say, if you can output the J invariant of any of these 4 neighbors, assuming this is a degree 3 graph example, then you win. So our conjecture is it seems to be hard, and we will briefly explain why the previous 2 methods over the finite field don't work. And I know this is like a Friday afternoon, and also Black Friday is also introduced in Belgium, so people are tired. So let's take some quiz. So yesterday I went to the M Museum, and this museum is really interesting because not only it gives exhibitions. How many of you have seen these 2 pictures? Yeah, at least 1, 2. Yeah. And they also ask you questions to give you deep thoughts. They say, what similarities can you see between these two works of arts? Any ideas? Ah. Do you want to try?
Shape.
Shape? What about the shape?
I mean, it's a rectangle-like or even square.
Yeah. It turns out that's also my naive observation. That's the only relation I can find between these two pieces of arts. Right? So if an artist say this is a piece of art, this is a piece of art, and so yeah, they are square. So if they are square, what reminds you is you need to take a square root, right? And in general, you need to solve a high-degree polynomial. Right? So the reason we conjecture that the problem is hard is because the previous two methods or any related method you can think about, they both require to solve a high-degree polynomial. Degree is relevant to the degree of L. Right? Yeah, and we also look into other methods which are, more like analytic, work over any field which doesn't require solving polynomial, and we list a number of cryptanalytic attempts saying why they don't seem to work. We also have a proof that, so this is the special case, as I say, if you define the isogeny graph as gluing two volcanoes with the same structure together. If you work in the general case, so it's not necessary that the J invariant is the CRT component. Well, of course, it's still the CRT components, but it's the CRT component of two not necessarily identical volcanoes. So in the general case, you can also prove if you can find the neighbor, if there is an algorithm that allows you to find the neighbor, then there is an algorithm to solve RSA. Oh, sorry, to break factoring. Over the special case, we don't know how to prove that it's equivalent to factoring because we don't know how to produce. We don't know how to produce two graphs with the same structure without knowing the modulus.
I'm confused.
Yeah.
I might just be stupid. Your two methods. Your two definitions of the modern isogeny thing. One you says, I just take J invariance mod P, J invariance mod Q, and I glue them together. Yeah?
Yeah.
And then the other one is I've got solutions of this
Modular polynomial.
Polynomial.
Yeah.
So
what are the difference?
why are they different? Yeah.
So the difference. So this part is the same. So far, what you said is the same. The second case, we assume we are only looking at subgraph where they overlaps. In other words, the more general case, when you take the composition, they don't necessarily correspond to the curve with the same endomorphism ring. So in the second case, we assume we are only looking at the subgraph where the J invariance corresponds to elliptic curve with the same endomorphism ring.
Oh, okay.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Okay. Yeah.
Okay. All right. So that's breaking down the detail why both two methods require solving a high-degree polynomial. All right. So more pop quiz. So in the real, so the more pop quiz is actually just making the first problem more complicated. So suppose right now you are not only given one J invariant. You are given two J invariant. One is called E0, let's denote them J0 and J1, and then you know they are L isogenous. So instead of finding a neighbor of a single curve, right now you are, let's suppose you are given more information. So how about finding their joint neighbors? Say if you are, I was asked you to find the curve which are 3 isogenous to E0 and the 9 isogenous to E1. So let's look at who are the candidates. So there are 3 candidates. So this guy is satisfied the relation that is 3 isogenous to E0 and 9 isogenous to E1. So does the other 2. So suppose now I make the problem give you more information. and find the task is to find the joint neighbors. Excuse me. So it turns out this problem also seems to be hard, because the natural method we can think about is you try to solve a system of equation, right? One is the neighbor defined by the modular polynomial of degree L with one input as J1 and the x as the unknown variable. The other polynomial is the modular polynomial with degree L squared with one input as the J invariant of E1 and the other variable as x. It turns out that if you take the GCD of these two polynomials, it's still a nonlinear polynomial. It has degree L, not 1. So it still requires to solve it over the RSA modulus, which we still don't know how to do. But in some cases, if I give you two elliptic curve, and it turns out the joint relation only have one unique solution. So for example, if I give you E1 and E2, I ask you to find something which is L isogynous to E2 and M isogynous to E1. Then you take the modular polynomial and do the GCD. In fact, they only have one unique common root. So in this case, you can actually solve the joint neighbor problem. So just to jump ahead to the actual group construction, we are going to use the hardness of the first joint neighbor search problem as the hardness for inverting. Because if you remember the previous graph, if I fix E0 as the identity, then the inverse of E1 is the E2 over here. And we say this is hard if I give you E0 and E1. And we are going to facilitate the efficiency of composition by the second problem. So if I can make sure that when you compose, they only have one unique resulting composition points, then it's easy to compute the joint neighbor. So with this idea, let's go to the formal construction of the group with infeasible inversion. So it's actually a trapdoor group with infeasible inversion in the sense that you need the trapdoor P and Q to sample all the J invariants. So the trapdoor is P and Q, and we need to decide a discriminant in the beginning, which decides the endomorphism of all the curve we are interested in. And the public parameter is n, and the representation of the group identity E1. So encoding of a class group element looks like following. So we can think about it as a canonical way of encoding a class group element. As we said before, it's a unique J invariant. After you fix E0, it's everything else is a one-to-one isomorphism. But to facilitate the composition, we need to encode all the elements as polynomially smooth ideas that are co-prime to each other. Because when they are co-prime, you can show that their composition is unique, and you can take the uniqueness to do the GCD and let the linear polynomial, the root, be the composition result. So it's not an ideal way of encoding group with infeasible inversion. It has condition. That infeasibility of inversion is conditioned on you don't actually accidentally output the inverse, and you make sure everyone else is co-prime to you, and it's hard to find the inverse from the encoding of E1 and other source. And the feasibility of composition is when it's guaranteed when the norm of different encoded elements are co-prime. Then when they are co-prime, you can show that the GCD of the modular polynomial is linear, so you can efficiently compute the root. Okay, so there are a lot of difficulties in generating the parameters efficiently. So first, you need to actually we require elliptic curve with endomorphism ring with a large discriminant. So if you first fix the discriminant, which is potentially exponentially large, then actually finding an elliptic So finding an elliptic curve with such a fixed large discriminant is as itself a hard problem. The known method, which is called the CN method, only works when D is a polynomial in theory, and in practice it's relatively small. So what we can do is we let the discriminant not be an ideal, which is the imaginary quadratic field, with an ideal class group imaginary quadratic order, which means it has a lot of small factors. So we're going to find a curve on the crater. They go down the hill to find actually a curve which doesn't necessarily live on the crater. If you create it that way, then the order of this class group is still large enough, and we still need to make sure this order is hidden, because otherwise you can actually solve discrete log to break the inversion problem. And to make sure you can encode, you also need to be able to sample element with small norm. This needs a short relation basis of the class group. You can do it in practice with the new record achieved by also two researchers here with a relatively middle-sized D. So in practice, you can assume something which is not efficient in theory, but you can reach to a degree where it's able to implement the parameter. So by the way, we didn't do such a big example. We only do examples with discriminant like 10,000 to test the functionality.
But you keep your short relation basis secret, yeah?
Right.
Yeah, okay, so that's part of the secret case.
So in some sense, you can. That's the next slides. What we assume is hidden is you need to assume the discriminant is also hidden, because otherwise you can compute that offline. And the group size is hidden. The number of points on E0 is hidden. The P and Q are of course hidden. Well, these are the four things we mainly assume are hidden. There are a lot of details in the actual paper. So that's almost the end of the talk. The summarize is we propose a candidate trapdoor group with infeasible inversion from elliptic curve isogeny. So this work will appear in AsiaCrypt this year, and it's also available on ePrint. The main assumption is this problem called L and L square isogenious neighbor problem is hard over RSA Moduli, and the potential application of group with infeasible inversion include broadcast encryption, directed transitive signatures, and maybe more. And thanks for your time.